From a student's perspective, ethers are pretty much your dream functional group. They don't react with bases, they don't react with nucleophiles, and there's only one reaction of synthetic significance that we need to deal with in introductory organic. When a symmetrical ether is treated with hydrogen halide, alkyl halides result. The hydrogen halide may be HBr or HI. These are the two hydrogen halides that have nucleophiles strong enough, bromide and iodide, to make this reaction happen. And notice I slipped in the word symmetrical here. When these R groups are identical, we actually make 2 moles. This same reaction occurs if the alkyl groups are not identical. The problem is that then we make a mixture of 2 alkyl halides, and for synthetic purposes, this is problematic. So typically, we'll use this for synthesis when we're starting with symmetrical ethers. How can we rationalize this reaction? Well, let's take a quick look at the mechanism. I've written an ether here that has primary alkyl groups, and that's important. And of course, oxygen has 2 lone pairs of electrons. I'm going to put 1 there. And in the presence of strong acid, that ether oxygen is protonated. We can follow that with arrow pushing. A pair of electrons forms a bond with hydrogen. This bond breaks to make halide. So this is an equilibrium reaction that makes a protonated ether. It turns a very poor leaving group, alkoxide, into a good leaving group, alcohol. So now we can expect that an SN2 reaction will take place with a primary alkyl group with the halide that results from the protonation reaction using a pair of electrons to act as a nucleophile. So the result is an alkyl halide plus an alcohol. But we said there are 2 moles of alkyl halide made in this reaction. Well, that's because this alcohol is also reactive with HX. We talked about that when we talked about alcohol chemistry. So let me take this mole of alcohol that was made in this reaction and write it right down here. And again, we'll picture a reaction with HX, protonation on oxygen, in an equilibrium reaction, which we can track with our arrow pushing. And now we have a good leaving group. So another SN2 reaction happens, displacement of water by the halide. And we can track that pair of electrons with arrow pushing to watch the SN2 reaction make a bond with carbon as the water leaves. And I keep calling this an SN2 reaction because it's at a primary carbon. So here we have it. We've made 1 mole of alkyl halide and a 2nd mole of alkyl halide. That 2nd mole is made because the product in the first step of primary alcohol is also reactive with HX. Let's take a look at what happens when we have an ether with tertiary alkyl groups. The reaction mechanism changes when we have tertiary alkyl groups attached to the oxygen. We still make 2 moles of alkyl halide, and we still start out the reaction by protonation of the oxygen. We'll track the bond forming with arrow pushing and bond breaking. This makes the halide that will react later as we protonate the ether in an equilibrium reaction. Now once again we've made a good leaving group. The difference is that it's attached to a tertiary carbon rather than a primary carbon. So this results in an SN1 reaction. We simply picture the cleavage of this bond. Nothing's forming. As that leaving group leaves, here's the alcohol, to make a carbocation. And then we know that these tertiary carbocations are real reactive with nucleophiles. So it's no surprise to us that in the presence of that halide we made, the carbocation makes an alkyl halide. But wait, once again, we've just made a product in this reaction that is also reactive with HX. Let me rewrite the product alcohol we just made right here. And as we just said with the primary alcohol, this tertiary alcohol is protonated. As you see above, in an equilibrium reaction, we again make a good leaving group, water. And because we have a tertiary alkyl group, that water leaves in an SN1 reaction, just like above. We can track those electrons. In bond breaking, we lose a molecule of water, and make the carbocation, which, just like above, will react rapidly with the halide to form a new bond. And so again, we see that in fact we do make 2 moles of tertiary alkyl halide, as we wrote in our equation up here. Okay, so we looked at primary ethers, we looked at tertiary ethers. What about secondary ethers? Now we've got 2 alkyl groups attached to the carbon, and this complicates things because you may recall that secondary carbons lose leaving groups in SN1 and SN2 reactions. So we can expect a mixture of both. And the exact structure will determine whether there's a lot more of SN1 or a lot more of SN2. But in any case, the result is the same. We treat a secondary ether with HX, and we make 2 moles of the secondary alkyl halide. There's one more case that's a bit of a ringer that I want to look at quickly. When we have an aromatic ring as one of the groups attached to the ether, we'll make 1 mole of an alkyl halide and phenol. Phenols are not reactive with HX, so unlike the other cases, this hydroxyl product does not react with the HX in the mixture. So under these conditions, we'll see a phenol of some kind. This is phenol itself, and an alkyl halide. So there you have it. Ethers cleave when treated with HBr or HI to make 2 moles of an alkyl halide. Symmetrical ethers make a single product. Unsymmetrical ethers make 2 alkyl halides.